Hello everyone, I'm Nathan from Team 53 presenting on an NDL project that is enhancing the PV cell performance by predicting the junction temperature in order to optimize the cooling systems. So the problem statement, as we can see here, is basically to reduce the high junction temperatures which exists in PV cells. It can lead to two problems here. That is, the cell output is reduced due to the high temperatures, the derating factor, that is the temperature, and the lifespan of the PV cell. And the PV cell is a very costly device, we need to ensure as a long lifespan as possible. So as we can see from the graph, at very high junction temperatures, the output power reduces drastically, and the lifespan of the PV cell will also reduce. As you can see from the graph, from here, the power output reduction occurs, and the efficiency will also reduce along with it. So the traditional methods of temperature monitoring, that is array tracking, etc., are very inaccurate and or costly at the same time, which leads to a lot of related expenses. So, an inaccurate temperature predictions, which are caused by these traditional systems, lead to suboptimal cooling strategies, which, as we know, harms the lifespan of the PV cells. So our solution in this case is predictive modeling, which uses historical data for prediction, so which leads to an optimized cooling. Our data set here uses two inputs, that is the solar irradiance and the ambient temperature, and we get the output as the device temperature, which we can use to create cooling systems which improve the efficiency and the lifespan of the PV cell. So this slide details the process that we have followed for this uh, predicting prediction. The step one is we utilize historical solar irradiance and temperature data, as I had mentioned before. This will give us a baseline, give us the data to make our baseline model of. Then we develop the model to predict the PV junction temperature, which is then integrated with a real-time control system in order to provide real-world cooling systems. And then we optimize the available cooling resources which are currently used in order to maximize the efficiency. Hmm. Up next, we have the model itself. Since our data is numerical, both the solar irradiance and the ambient temperature, the solar irradiance, which is the CMP22 that we have used, obtained from the pyranometer, and the ambient temperatures, which we have gotten from NREL data. And so linear regression is being used for the baseline model. uh, to measure the accuracy of the model, we have used metrics such as the mean squared error, the R square, and explained variance score. For a baseline model, we have got an R square that is which is accurate at about 94%. For the next phase of the project, after the baseline model has been created, we use random forest regression to improve the accuracy. On using the same metrics to evaluate model performance, we have an accuracy of about 98%. Up next, we can see the visualizations of the data. This is the incoming data that we have of CMP22 irradiance. As you can see, the solar irradiance has been plotted against the months of the year. The solar irradiance over the years from 20 to 23 historically have followed the same trends over the 4 years that we have taken it over. And then visualizations of the data, as you can see, these are the actual versus predicted values for both a baseline, that is the linear regression, and the next model that we have used of random forest. As you can see from the visualization of the random forest algorithm, the actual and predicted values are very narrow. Um, and what we propose for the next phase of the project to optimize the model, we are using ADI boost to better predict values and improve the accuracy. And finally, coming to the results of our project, we can see we have a 0.98% variance of R square, which shows a very high percentage of variance in the target variable. Thank you. This has been Team 53.